Section 9.4, the pigeonhole principle. So here, this problem was first come up with regarding pigeons, which is why we call it that. So here, for example, we've got 5 pigeons, and there's 4 holes that they could go into. Well, that means that one of the holes is at least one of them, will have 2 or more pigeons. And you can hear a little bit there about the detail of where that comes from. But this is a principle that we can use surprisingly often. So let's say we've got a group of 6 people. Must there be at least 2 who were born in the same month? In a group of 13, must there be at least 2 born in the same month? And in that case, how is that going to actually work out? Well, if we've only got 6 people, we don't necessarily have 2 that were born in the same month. We could have January through June. There's no repeat. But there's 12 months. So if we get up to 13 people, since there's only 12 months, there must be a repeat in there somewhere. And this is using that same pigeonhole principle to think about it. Again, you could think about it by picturing it. I've got 13 people, I've got 12 months, and I'm trying to put each one into them, and I am going to have at least one overlap. Let's see another example. Let's say we've got residents of New York City. Must there be at least 2 people with the same number of hairs on their heads? Well, this is getting a little bit trickier. We're dealing with much larger numbers here. Now, we're not going to necessarily get the exact number. I'm going to use 8 million here as simplicity. You might have to do a little bit of Googling on this, but the maximum number of hair on a person's head is basically 300,000, and that is less than that. So anytime that second number is less, we're going to have this pigeonhole problem. The first number I've got is more, the second number I've got is less. And we're going to describe this mathematically as it is not one-to-one. Again, we're going to have at least 2 arrows going to the same number. All right, let's look at that as an application for decimal expansion. So, as you remember, if you've got that little line above those, that means those are the repeating digits there. And any decimal expansion either terminates or repeats. Here would be a terminating one. This would be a repeating one. And what does the actual decimal expansion look like? So here I've got 3 divided by 13, and you can see as I'm starting to expand that. So, what are our possible remainders? Remember, the remainder is always going to be smaller than the number being divided. So I could have a remainder of 0, or I could have all the way up to 13, 1 less than 14. And as you can see here, here's my sequence of remainders, and here are my actual values. Well, if this sequence of remainders repeats, in other words, it keeps going, I will have, again, at least 2 of them that are going to go to that same value. So again, here as we can see, 1, 4, 2, 8, 5, and 7, those repeat forever. So again, we are going to have infinite ones, infinite 2s, infinite 4s, and so on. So let's take that pigeonhole principle and try and generalize it a little bit. So here I've got n pigeons, m pigeonholes, and here I've got some generic positive integer k. So k times m is less than n. Then at least one pigeonhole contains k plus 1 pigeons. And do note that's the minimum number. It might have more of them. So here I've got 4, 9, and 2 as my example. So as you can see, I've got 9 pigeons, I've got 4 pigeonholes. And so I've got 4 times 2, which is of course 8. That is less than 9. So at least one pigeonhole is going to contain 2 plus 1, in other words, 3 pigeons. And you can see at least one example of what that's going to look like. again, there's that same principle written out generally. All right, so let's talk about initials. So I've got a group of 85 people, and at least 4 of them must have the same last initial. So how do we show that? So again, I've got 26 possibilities for that last initial. So again, I've got 85 people over here, and those are my pigeons. My pigeonholes are the 26. Those are the actual letters that we could have, A through Z. So if I do 3 times 26, that is 78. If I multiply by 4, I'd get larger. So 3 is the number I'd want there. And so that means that 3 is that final number in my pigeonhole problem. So again, we're going to add that plus 1 and say that at least 4 people must have that same last initial. And again, here is that generalized pigeonhole principle stated out once more.